a little embarrassing this morning. So because it's a neat thing and I want you to see it, um, I decided to make a little video here where we make that substitution in the Cauchy-Euler equations. And it also gives me an excuse to finally prove the Euler identity that I promised a while back, and kind of recap power series, which will be useful going forwards. So the place I got hung up on in class today, I really wanted to work it all out in the prime notation, because the prime notation is really my preferred notation for derivatives. But because we're substituting for the independent variable here rather than for the dependent variable, there's really no clear way to do that. And it's my fault for getting hung up. So I hope that you guys get something out of this. Of course, the mechanics of solving the thing are what we saw in class. You come up with a characteristic polynomial, and then depending on whether you've got distinct roots, repeated roots, or complex roots, you write down your answer. It's really not that complicated to solve the homogeneous Cauchy-Euler equations. And then, of course, if you have a non-homogeneous Cauchy-Euler equation, just use variation of parameters to get your particular solution. So let's go ahead and take a look at this kind of neat trick. Substituting to transform Cauchy-Euler equation into constant coefficient. That's the game here. So I'll do this with a second order equation, and I'm not working with the right-hand side at all. So we'll take ax squared y prime prime plus bx y prime plus cy. And first, maybe I'll just rewrite this in the other notation. This is d2y over dx squared plus bx times dy dx, the Leibniz notation, plus cy. Because we're subbing for the independent variable rather than the dependent variable, it's not clear what the prime would indicate in either situation. So the substitution I'm going to make is x equals e to the u. Which is equivalent to saying that u is equal to the natural log of x. So this is sort of our guiding principle, letting some new variable be the natural log of the old variable. And that's what we saw in class when we worked out through reduction of order. The pieces that we slap on when we had repeated roots were natural logs, whereas in the past, normally there would just be powers of x. So I'm like, okay, let me let some new variable be the thing I have powers of following my reduction of order formula. And at times it'll be convenient to think of it in either way. The big trick here is to use the chain rule. And the chain rule says that if y is equal to y of u and u is equal to u of x, then, where everybody is appropriately differentiable, then if I want to differentiate y with respect to x, right, kind of, I'm thinking of this is like y of u of x, then I differentiate y with respect to u, and then I multiply by the derivative of the inner function. In other words, here, puppy, sorry, but we got a new puppy, he's crazy. So here, y is really y of u of x, and I'm after puppy, get out. Yes, you're beautiful. No, you can't shoot a power cables. Really, y is y of u of x. So I'm trying to write dy dx in terms of du dx because I want to transform this equation into one that has du dx's in it. Okay. So that's the theorem, the chain rule from Calc 1. And now I'm going to apply it with u as the natural log of x. That's the idea. So for us here, with u equals the natural log of x, we get dy dx is equal to dy du times du dx, and that du dx. So dy du, I'm maybe not sure what that is off the top of my head, but du dx, I know that's 1 over x because u is the natural log of x. So this is dy du times 1 over x. Now that's what I mean when I say we're changing the independent variable. So my new equation, instead of having y's and x's, is going to have y's and u's, not u's and x's. That's what I had unclear, I guess, in my brain today during lecture. And the second derivative, d2y dx squared, would be what you get by taking the d dx derivative of dy dx. And by what we just did above, this is d dx of dy du times 1 over x, because dy dx is dy du times 1 over x. That's what we showed here. Now to do this derivative, we need to invoke the product rule because there's a product here. And we'll also need to be a little bit careful with the chain rule when I go to differentiate this guy, and I'll talk you through it. So first, the product rule. I'm going to leave the 1 over x alone and say, okay, leave this guy alone, differentiate this. That's 1 over x times d dx of dy du. And then I add that to what I get when I leave the dy du alone, and I take the d dx derivative of 1 over x, which is negative 1 over x squared. Now here, I want to differentiate dy du one more time with respect to the variable x. And this is another chain rule thing. So the idea is, I'm thinking of this as a function of u. So I would come in here and differentiate with respect to u again, but then u is a function of x. So I'm going to differentiate this with respect to u and then multiply by the derivative of u with respect to x. That's the idea. It's just the chain rule again. And if you think about it, you'll be able to make sense of it. So this is 1 over x times the derivative of dy du, a function of u. That's going to be the d2y du squared. Differentiate one more time with respect to u, and then multiply by the derivative of the inner, which is du dx. All right, so remember, u is a function of x, and y is a function of u. And then here I'll just have my minus 1 over x squared dy du. Du dx is itself 1 over x. We know that, right? Du dx is 1 over x. We've used that already. I guess I didn't write it explicitly here when I said here, du dx is 1 over x. We've used that. I'll put it up here. So what do I have all together? I've got 1 over x times d2y du squared times another 1 over x here, right? 1 over x d2y du squared times 1 over x. So this is really 1 over x squared. And then minus 1 over x squared times dy du. And we can factor the 1 over x squared out. And you get d2y du squared minus dy du. What this does is it gives me the second derivative of y with respect to x, the thing we normally just call y double prime, in terms of the second and first derivative of y with respect to the new variable u. And of course, I have dy dx itself in terms of dy du. So if I take these two and I plug them into my Cauchy-Euler equation, let me just copy those down. Actually, let's copy the Cauchy-Euler equation. Let's do it like this. Therefore, ax squared d2y dx squared plus bx dy dx plus cy is going to become ax squared times the second derivative dy dx was 1 over x squared times d2y du squared minus dy du. So this piece right here is 1 over x squared times the second derivative of y with respect to u minus regular old dy du. And then you've got plus bx times dy dx. Well, dy dx was dy du times 1 over x, or 1 over x times dy du. And then your plus cy is just chilling. That's still plus cy. And of course, the magic is that the x's cancel. This is a times d2y du squared minus dy du plus b times dy du plus cy. Puppy, Maxie, no shoes. I'm sorry, but come here. And now you notice that all the x's are gone, right? We don't have any coefficient functions that are non-constant. Yes, here, how about this? Let's play with this. And if you rearrange this and kind of put this back into the form we're used to seeing our differential equations in, this would be a times d2y du squared. And then you've got a plus b times dy du minus a times dy du. So that's plus b minus a times dy du plus cy. And this is constant coefficient. So it kind of interestingly, it's harder to substitute in some ways for the independent variable than it is for the dependent variable. That's a little odd. And I apologize to you guys for the lack of organization in this part of the lecture this morning. It's quite bad. You can see that the auxiliary polynomial for this is the same as the characteristic polynomial for the Cauchy-Euler equation. So the auxiliary polynomial for this would be P of m equals am squared plus b minus am plus c is the same as the characteristic poly for the original Cauchy-Euler. Remember the formula for the Cauchy-Euler characteristic polynomials, it's ar squared plus b minus a times r plus. So, yep. Solving this now would be the same as solving any other constant coefficient equation. You find your complementary solution. And that would give you, so suppose this has roots. Suppose m equals m1, m2. Our roots auxiliary polynomial above, then the solution call this guy 1. The solution to 1, the solution to the associated homogeneous equation, that left-hand side, 1 would be, just remember that the variable here is u, right? So this would be y equals e to the m1, so c1 e to the n1 u plus c2 e to the n2 u. And this is where thinking of things as x equals e to the u instead of u equals ln x is going to come back. So remember what we said earlier. We said, well, I'm making this substitution, but really the same as this substitution. We use this to cook up our derivatives, but now when I go to write down my answer, I'll use this. So e to the u, that's x. And then here, this would be, see, just a little algebra trick. This is e to the u all to the m1 plus c2 e to the u all to the m2. And that's c1 x to the m1 plus c2 x to the m2. And that's it. Right, this is the solution we expect from our Cauchy-Euler equation. This is how you would get it as the solution to a constant coefficient problem. And then you just use that the substitution, the x equals e to the u, or u equals ln x, so to go back and forth. All right. I'm gonna let that dog out real quick. Maxie, what are you doing? What are you doing? You're just feeling wiggly and crazy right now, huh? Come here, Max. Yes, James Clark Maxwell. Silly Clark. All right. Yeah, so that's the Cauchy-Euler thing from class that got a little bit out of hand today. I apologize again for that. The other thing I wanted to do, quick review of power series and the proof of the Euler formula that we've been using so much, the e to the ix thing. And then I can share with you some other cool stuff about that. So there's going to be a fast and dirty review of power series. Power series, these are expressions of the form sigma n from 0 to infinity an x to the and they're functions of x. Usually we use capital letters to describe the functions for power series. But yeah, so that remember what the sigma operator means. It's just a shorthand for a big long addition problem. So if you plug in 0 for n here, you get a0 x to the 0. And what sigma says is you're going to add that up to what you get with n equal to 1, which is a1 x to the 1. And then you're going to add that up to what you get with n equal to 2, which is a2 x squared. And you're going to add that up to what you get with n equals 3, 4, 5, all the way up to whatever this is. And in this case, it's infinity, so it's going to go on forever. These are infinite polynomials. Or polynomials of infinite degree. Think of it like that. Notice that there's no n's here. Right? The output doesn't contain any n's. In the same way that the output from the Laplace transform doesn't contain any x's, here you're summing over the n's, so the n's go away. The n's are an index. And when you're integrating in the Laplace transform, you're integrating with respect to x. So that is your index there, and it goes away. Power series have some convergence issues, just like Laplace transform or improper integrals can. These converge so that they possess something called each Our series has an interval and radius of convergence. So I should say this series is centered at 0. More generally, they could be centered at A. So here, I'll show you who's for a series like that. So if your series as above is centered at 0, then we would say that that your IOC, your interval of convergence, is going to be an interval symmetric about 0. The distance here from the center of that interval to its endpoint is called the radius of convergence. And this interval may be closed, may be left closed, right open, may be left open, right closed. Or any combination. Closed on the left, open on the right. More generally, the series could be written we can shift the center to any real number A. Let me call it C. Like this. I'll call this G of X. Be clear that it's not the same series as we had up there. If you write this guy out, he would look like A0 plus A1 times X minus C plus A2 times X minus C squared, and so on. You change the center without changing the coefficients, you definitely have a whole new function. Although you could readjust the coefficients to get the same function if you wanted. And these guys, intervals of convergence, if you're centered somewhere other than 0, picture is really the same. Here's C. Some distance R. And over here would be the X value is C plus R. And that same distance R way over here, C minus R. Anyway, the idea of these intervals and radius of convergence R is called the radius of convergence. And it's called that because it's the radius of the interval of convergence. So I, which would be equal to 1 of closed C minus R to C plus R, left closed, right open, left open, right closed, or the fully open. It's called the interval of convergence. Because if X is in that interval, the series is guaranteed to converge. And what's more, if you take an X that's not in that interval, the series will diverge. So it's puppy. Right. So the interval of convergence is the set of all X values that you're allowed to plug into the series. If you plug in something from that interval, you'll get a convergent series. If you plug in something that's not in that interval, you'll get a divergent series. So I can say that these series define functions in that sense. I can plug in for x. What I get then is a series of numbers which may or may not converge. And I'm only really able to treat this as a function if I'm considering those x values for which this series converges. We haven't talked about what it even means for a series to converge yet, because we're, again, quick and dirty review of power series. Remember, a series is said to converge. Series am, sum from wherever to infinity converges if the limit of partial sums is finite. I'll just say if it adds up to a finite amount, a fixed finite value. The details here are somewhat important. This notation is just a shorthand for addition. So the sum from n equals 0 to infinity of an, that's a0 plus a1 plus a2 plus and so on. It's an infinite sum. It's a series that goes on and on and on forever. So when I say that this adds up to a fixed finite value, what I really mean precisely, I'm not sure. Sigma n from 0 or wherever to infinity of an converges means that the limit as capital N goes to infinity of the sum from 0 to capital N, a sub little n, exists and is finite. And this is very much analogous to my then r to infinity integral 0 to r f of x dx from class. Right, so infinite series, very, very similar to improper integrals. They're basically the same thing. And then a power series is an infinite series, but with some powers of x in it. And there's a bunch of ways to think of them. For our class, the nice way to think of them is as no maxi, as infinite polynomials. Maxwell, come here, bud. You're very cute. Very sick, especially if we go like this. They're all wound up in your tummy. Come here. Oh. Sorry, it was just the sweetest thing. All right. If you don't remember enough about series to follow what I'm saying here, then you've forgotten quite a lot, and you really need to go back and address it fresh. I don't want to go any deeper into like basic definitions. So let's look at some examples of power series. That's what we're here to do, is talk about power series. Coming back to power series, if an is the constant function 1, then sigma n from 0 to infinity an x to the n, I'm going to center at 0 pretty much all the time. Maxwell. Maxi. Pretty much always going to center at 0. Then this would just be sigma n from 0 to infinity of 1 times x to the n, which is just sigma x to the n. What is this? This is 1 plus x squared plus, the next term would be x cubed, and it goes on and on forever like that. This is a geometric series, and as long as appropriate conditions are met, as long as the series converges, it will converge to 1 over 1 minus x. Geometric series, starting term over 1 minus the common ratio. But this is only true if x comes from the appropriate interval of convergence. And in this case, that's the open interval from -1 to 1. or absolute value of x strictly less than 1. Other series you may or may not remember. If we take an to be 1 over n factorial, then the series we're looking at is sigma n from 0 to infinity, 1 over n factorial times x to the n. So 1 over 0 factorial times x to the 0. 0 factorial is 1, so this also starts as 1. And then 1 over 1 factorial is also 1 times x. The next term there would be 1 over 2 factorial, which is 1/2 x squared. The next term would be 1 over 3 factorial, which is 1/6 x cubed. This guy, this is e to the x, and this is for all of x. The interval of convergence here is all real numbers. Other ones that you should remember, sine and cosine. Maybe one you don't remember. And is, let's see, let me just say it like this. Other important power series. Yeah, my wife's playing with the dog now, it's pretty cute. Negative 1 to the n over 2n plus 1 times x to the 2n plus 1. This is the inverse tangent of x, arctan, and your interval of convergence there is absolute value of x is, let's see, it only converges at the one end. Yeah, okay, so we can't write it like that. Actually, no, it will converge at both. Yeah, okay, yeah, I could say it's absolute value of x less than or equal to 1. If you plug in 1 or negative 1, it'll still converge. It's just a weaker convergence. And the sine and cosine series. Sine x negative 1 to the n is very similar to this, only you've got a factorial downstairs. Factorial x to the 2n plus 1. And cos x is sum n from 0 to infinity. Negative 1 to the n over 2n factorial x to the 2n. This guy and this guy I'm going to use in what follows. Oops, sorry. Okay, we know a series for logarithm functions, pretty much any rational function, because you can build those up out of products and sums of things like this. And we'll use power series from time to time in this class. The main thing I wanted to do for you is prove that Euler formula. So just reintroduce you to the notation of power series, the language of power series, and prove to you that formula that we've been using both in the constant coefficient equations and then today in the Cauchy-Euler equations. Let's do it. I promised this a while ago and never did. Yeah. E to the I, I'll use the variable theta, is equal to cos theta plus I times the sine of theta. I to the 0, the 0th power of anything, is 1. I to the 1 is I squared, remember I is the square root of -1, so I squared is -1. I cubed would be I to the 1 times I to the 2, which is I times -1, or negative I. I to the 4 is I squared times I squared, which is -1 times -1. So let's back up to here, and then things loop. So in other words, you can reduce powers of I mod 4. Every 4 they loop. So if you know where you are in that modulo 4 cycle, you can say what any power of I is. For example, I to the 100 has to be 1, right? Because 100 is divisible by 4. I to the 103 is the same as I cubed, because the remainder when you divide 103 by 4 is 3. So you just figure out where you are in this cycle, and I can tell you any power of I. That's the preliminary. The other preliminary are those power series. So e to the I theta is what we would get when we take the power series for e to the x and plug in I theta. So this is I theta to the n over n factorial, right? 1 over n factorial times x to the n. I'll just write these terms out. This is I theta to the 0 factorial plus I theta to the 1 factorial plus I theta squared over 2 factorial plus, I'm going to write out a bunch, I theta cubed over 3 factorial plus I theta to the 4 over 4 factorial plus I theta to the 5 over 5 factorial plus I theta to the 6 over 6 factorial plus, and so on. We'll figure out the first 7 times x, 7, 0. I'll leave the factorials as factorials. We're going to clean up the other stuff as much as we can. The big deal is popping out the appropriate powers of I. So this first guy is theta to the 0 over 0 factorial. And I have plus here I times theta over 1 factorial. That's I to the 1 is I squared. That's going to be minus theta squared over 2 factorial, because I squared is -1. And then I theta cubed is going to be minus I theta cubed over 3 factorial. That's I cubed is -I. I to the 5. Okay, where's I to the 4? I to the 4 is 1 again, so this is plus theta to the 4 over 4 factorial. I to the 5 is the same as I to the 1, right? If I run back around here at 4 and then keep going up. So this is plus I theta to the 5 over 5 factorial. I to the 6 is the same as I squared is -1. So this will be minus theta to the 6 over 6 factorial. The next term will be I to the 7 times theta to the 7 over 7 factorial. What is I to the 7? 7 is 3 mod 4. So it would be minus I theta to the 7 over 7 factorial. It will go on like this. Okay. The magic here is that you now group terms according to whether or not they have i's in them. So this does not have an I, this does not have an I, this does not have an I. In fact, all the even terms don't have i's. These. So here we have theta to the 0 over 0 factorial minus the next orange term is theta squared over 2 factorial, and the next orange term is plus theta to the 4 over 4 factorial, and then minus theta to the 6 over 6 factorial. And the next even term after that would be plus theta to the 8 over 8 factorial. You see the pattern. And then the terms that have i's in them, I'll factor an I out. And what would be left is theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial, and so on. The next term would be plus theta to the 9 over 9 factorial. And each of these are reasonably familiar with the power series that you should all know from Calc 2 is one of our known series. This first guy is the series for cos theta, and the other guy is the series for sine theta. And that's the proof. So it's really not too bad. Most of it comes down to understanding how powers of I work and knowing the 3 relevant power series, the e to the x, sine x, and cos x series. Once you know that, you just plug and chug. It's nice and simple. A corollary is that I can write sines and cosines. I'll use the variable x again now. Cos x is e to the ix plus e to the minus ix over 2. Sin x e to the ix minus e to the minus ix over 2. This is useful in a lot of ways. One of which is if you have to integrate some nasty sine cosine stuff, write it like this. Your Calc 2 teacher didn't show you because he wasn't allowed to, or she wasn't allowed to. Can't stop me from doing that. You remember those damped harmonic oscillator integrals like e to the 5x cosine 3x? Way easier if you write them like this. Proof here. So you know that e to the ix is cos x plus I times the sine of x, which means that e to the negative ix would be cos of negative x plus I sine of negative x. And then because cosine is even, this is cos x, and sine is odd, this is minus sine x. Now just add these up. So e to the ix plus e to the negative ix is this whole thing plus this whole thing. It's 2 cos x. If I subtract them, e to the ix minus e to the minus ix, this minus this, the cosines go away, and this time I get 2I sine x. Oh, shit, did I leave up? Yeah, there should be an I down here. Sorry. 2I. Okay, and that's the proof. Divide both by whatever you need to isolate the trig function. There's a million other ways to use this. Sometimes people call these the backwards Euler formulas and call the first one the forwards Euler formula. It really says the same thing. The last thing I'll point out is that one last corollary. Why do people like hyperbolic trig functions? Well, remember, Cauchy of something is e to that thing plus e to the negative version of that thing over 2. So Cauchy of ix is actually just cos x. And sinh sine hyperbolic of ix would give you this, but without the I downstairs, right? Take sine sinh, which is e to the x minus e to the minus x over 2. Then that would give you not quite sine, but I times sine x. So the hyperbolic trig functions give us a means of going back and forth from complex arguments to real arguments through this kind of backwards Euler formula thing. I'll leave the proof here as an exercise for you. You don't need power series, you just use the formulas above and the definition of Cauchy and sinh. It's really not even really a thing to do. All right, that's the quick and dirty power series refresher. And the Cauchy-Euler substitution revisited. I hope you guys have a good day.